Section 3.2, Solving Systems of Equations Algebraically. On the previous section, we learned how to solve systems of equations by graphing. That's a very good procedure to use as long as the solutions are integers. In other words, we can graph them and determine that they are on a x and a y that we can actually identify. If they are somewhere in between, for example, an x coordinate of 2 and 3 and a y coordinate of 5 and 6, we really can't determine the exact value. Therefore, we need to find a different way of doing it, and that would be algebraically. In this section, what we're going to look at is to solve the systems of equations by substitution. And this is the procedure that we want to use. We want to copy the two equations. Number two, we want to select one of the two equations and solve for x or y. This could be two other variables. For example, if our system is dealing with A and B or C and D. This is your choice, but look for easiest equation to solve for. This is done by solving for the x and y that has a coefficient of 1, if possible. In other words, you're going to have to get used to seeing which equation is the easiest to solve for. Number three, substitute that expression into the other equation. This will give you an equation with one variable. Then we solve that equation for that variable, and then we substitute the value we get for that variable into one of the two original equations. Let's look at our first example. Here they want us to solve the system by substitution. We're given 3x plus 2y equals 9 and x plus y equals 3. Again, we need to copy the problem, which I already have done here. We need to choose an equation and then select a variable inside that equation to solve for. As you can see, it's our choice. I'm going to choose the bottom equation because the coefficients of one or both of the variables is 1. So if I write x plus y equals 3, and then it's my choice again to choose a variable to solve for. It doesn't matter which one, since both of them have a coefficient of 1. I'm going to choose x to solve for, so I'm going to subtract y on both sides. That will give me x equal to 3 minus y. Now, I take the expression that is equal to my value of x and substitute it in to the other equation that's in the system. So I have 3x plus 2y equals 9. And I know the value of x from the previous equation that I solved for. The value of x is 3 minus y. So I'm going to take that value and substitute it into that x. So I'm going to have 3 times 3 minus y. And I'm going to put that in a set of parentheses. Then I just bring down the rest of the parts of the equation, which are plus 2y equals 9. Now I have an equation with one unknown, and I know how to solve that. I simplify the left side of the equation by distributing 9 minus 3y plus 2y equals 9. Still simplifying, combining like terms, I get 9 minus 3y plus 2y is a minus y equals 9. Subtract 9 on both sides, and I get a negative y equals 0. Divide by a negative 1, and y is equal to 0. Now, I just take that value and substitute it in to our previously solved equation. So, x minus 3 minus, now we know y is 0. Therefore, I know x is equal to 3. So if I would have graphed these two equations, I would have had integers, and therefore it would have intersected on the graph at 3, 0. Our next example, again, solving a system of equations by substitution. We're given 8x minus 1 equals 4y, 3x equals y plus 1. We have to choose an equation and one of the variables in that equation to solve for. I'm going to choose the bottom equation. Why? Because it's always easier to solve for a variable that has a leading coefficient of 1, and that happens to be the bottom equation. So here I'm going to solve for the variable y, and I'm going to subtract 1 on both sides. When I do that, I'm going to get y equals 3x minus 1. In this equation, I know that the value of y is equal to this expression. Now, I'm just going to take this expression and substitute it into my other equation. Here I'm given 8x minus 1 equals 4y. I know the value of y in my previous equation. I noticed 3x minus 1. So I'm just going to take that expression and substitute it in for y. 8x minus 1 equals 4 times the quantity, and I use the expression 3x minus 1. Now I have an equation with one variable, and I know how to solve for that variable. I just simplify. 8x minus 1 equals, distributing, I get 12x minus 4. Now I'm going to subtract 12x on both sides, and that's going to give me a negative 4x minus 1 equals a negative 4. Add 1 on both sides. That gives me a negative 4x equal to a negative 3. Dividing by a negative 4, and I get x equals a positive 3/4. Now I take that value and substitute it into the other equation. Y equals 3 times 3/4 minus 1. That's going to give me y equals 9/4. Then I need a common denominator. That's going to be 4 over 4. Still has the value of 1. And I get an x value of 9 minus 4, which is going to give me 5/4. Therefore, if I did graph this, I would get a value or an intersection at 3/4, 5/4, which would be very difficult to predict on a graph. That's why we use an algebraic procedure to solve this systems of equations. Our next example, solving systems by substitution, we are given 3y plus x equals a negative 1, and x equals a negative 3y. Here, we already have a variable that is solved for. So I'm just going to use that and substitute it into the other equation. So I have 3y plus x is equal to a negative 1. Substituting our value for x, which is a negative 3y, I'm going to substitute into the equation. 3y plus, for x, a negative 3y equals a negative 1. When I solve this, I'm going to get 0 equals a 1. And we know that this is a false statement. Therefore, what do I know about these two equations? I must know that these two equations are parallel. And how do I know that? I know that from our previous section that the only time I got a situation when I had no solution is my two lines had to be parallel. So if I would take these two equations and solve for y, on the top one, I would get y equals a negative 1/3 x minus 1. On the bottom one, I would solve for y. I would get y equals a negative 1/3 x. Here I know I have slopes that are the same. And I know anytime I have slopes that are the same, and when I have y-intercepts that are different, I have lines that are parallel. Here I would graph my y, where this slope would be a negative 1/3 with an intercept of 0, 0, would look something like this. And this slope is a negative 1/3, but the intercept would be at 0, negative 1. That line would look similar to this. And there I have my two lines that are parallel. Now, when doing an algebraic procedure, I don't need to do all of this work solving for y and graphing. But we need to understand that when I get a statement that we know is false, then I know that I have an answer that is no solution, And that is because my lines are parallel. Let me just fix one thing in this problem. This would be a -1. But still, our statement is false, which generates no solution. Our next example, solving by systems, we have 5b minus 2 equals 2a, 3a plus 6 equals 2b. Here we have two different variables other than x and y, but we're still going to follow the same procedure. I need to select an equation and a variable in that equation to solve for. Here, I don't have a variable with a coefficient of +1, so I'm going to try to select what I think would be the easiest one, which would probably be the top one. So I'm going to have 5b minus 2 equals 2a. A is already isolated, so I'm going to divide both sides by 2. That's going to give me a equal to, 2 has to go into both, whether it goes in evenly or not, 5 over 2, or 5 halves b minus 1. My expression for a is 5 halves b minus 1, and I need to substitute that into my variable in the second equation. So I have 3a plus 6 equals 25b. Substituting the expression in for a, I get 3 times 5 halves b minus 1 plus 6 equals 25b. Simplifying the left, I'm going to distribute. I'm going to get 15 halves b minus 3 plus 6 equals 25b. Let's simplify again. 15 over 2b. -3 plus 6 is a +3 equals 25b. Let's subtract 15 halves b on both sides. That's going to give me 3 equal to, here I'm going to need a common denominator, so I'm going to multiply the top and bottom, which is 25 over 1 by 2, 50 over 2 minus 15 over 2. And when I solve that, that's going to give me 50 minus 15, which is going to give me 35 halves b. Now, I'm just going to multiply both sides by 2 over 35. And that's going to give me b equal to 6/35. Now I take that value for b and substitute it into the other equation. A equals 5 over 2. B is 6/35 minus 1. When I simplify, that's going to give me 7 3/7 minus 7 over 7, which is still the value for 1, which is going to give me a -4/7. So my solution as an ordered pair would be a -4/7, comma, 6/35. Our next example, 3x plus 2y equals 4, y equals a -3x plus 2. Again, solving by substitution, we already have a variable that is solved for, so I'm just going to use that expression and plug it into the other equation. So I have 3x plus 2, and for y, I'm going to use the expression a -3 halves x plus 2 equals 4. Let's simplify by distributing the 2. I have 3x plus 2 times a -3 halves is a -6 over 2, which is going to give me a -3. X, 2 times 2 is 4, equals 4. Now that's going to give me 3x minus 3x, which just gives me 4 equals 4, because these two variable terms cancel. This gives me a statement that is true. And if we recall from our graphing section that when we had a true statement, our two lines turned out to be the same line where they coincided. Well, let's solve this other equation for y. And when we do that, I get y equals a negative 3 over 2x plus 2. Therefore, I know that my slopes are equivalent, and I know my y-intercepts are equivalent. So therefore, I know that I have a line that looks like this. And if I graph both of them, it would just turn out to be the same line. Therefore, all points on this line are the solution to these systems of equations. And I know I have one line generated from the system when I have a statement that is true.